Hey guys, Trey here. Wanted to kind of do something different today. Usually we look ahead at the upcoming day's severe weather potential and do a forecast discussion, but wanted to take a look back today at last night's tornado event, sort of surprise tornado event in southwest Kansas. There was this beautiful tornado from an kind of an unexpected supercell that formed in southwest Kansas. You can see the radar and velocity imagery on the left and a couple of incredible images on the right. Just beautiful, kind of compact supercell structure with that tornado underneath. So this was a pretty surprise event. So I wanted to kind of go over some archived products, archive mesoanalysis, sounding data, etc., and try to figure out why this tornado happened and why nobody was chasing it. It was again a pretty unexpected event. This was the 13Z convective outlook from the SPC. As you can see, the area of southwest Kansas in just a general thunderstorm risk, and that was maintained throughout the day. This is the 20Z outlook, still southwest Kansas in a general thunderstorm outlook. So very little was expected from any severe weather. Not really expected in southwest Kansas. Even when the storm started to form and the MD came out, there was pretty much no talk of any tornadoes happening at all. Pretty much weak shear, but very steep lapse rates, large instability, with long straight photographs indicative of splitting supercells, but mainly just a damaging wind and hail threat. So this was issued at 6:32 p.m., shortly before the tornado touched down near Satanta, Kansas. So let's go ahead and take a look at some products here. Again, this was the HRRR model 18Z run from yesterday. It really didn't show much. It did show an attempted initiation of some thunderstorms in southwest Kansas down into the Oklahoma Panhandle by 0Z, but they were very short-lived and pretty much non-severe. And as we move on toward, here's the 22Z HRRR run, still shows some very minor thunderstorm activity down in southwest Kansas with a few stronger storms up in west central and northwest Kansas, but nothing really down here in southwest Kansas where the tornado actually formed. So here is the satellite imagery. This is a loop. You can see we had a morning complex of storms moving through Missouri and Arkansas down into Mississippi that produced an outflow boundary that moved through central and eastern Oklahoma. We had, by pretty much midday, we had a nice cumulus field developing all across western Kansas, and then those couple of storms really explode by 23 to 0Z. And they didn't last long at all. They did not last long at all. They lasted maybe an hour or so at most before they died. The tornado was fairly brief. But let's go ahead and dig in here. So we can see on satellite we have this outflow boundary moving through central Oklahoma. Whether or not this played a factor in tornado genesis is kind of unclear. The complex of storms was well out here in Missouri and Arkansas, but you can see the boundary extending well into central Kansas at the start of that loop. So did the western portion of this boundary kind of stall out here and kind of aid things? It's hard to say. What we do know is, here's our surface map. We did have very significant upslope flow in southwest Kansas that was kind of wrapped around a center of low pressure located over the northeast Texas Panhandle and northwest Oklahoma. Kind of a dry line bulge there as well, 40s and 50s dew points behind this sort of bulge, and then up in southwest Kansas we had upper 60s dew points, which when you have upslope flow, and a lot of people don't really know that southwest Kansas is very much elevated above the rest of Kansas. Here's a topographical map. These reds, oranges, purples, and the whites out here, that is increasing elevation. So you have very much increasing elevation to the east as you go toward Colorado. And so anytime you have easterly flow, you're going to get some help from the terrain, some lift from the topography, and that, I believe, played a big role in why storms were able to form here in southwest Kansas. You got nice moist upslope flow, and when you're at this kind of elevation, of course it's not Denver elevation, but it is definitely elevated over the rest of central and eastern Kansas. When you have 60s, upper 60s, and even low 70s dew points in this terrain, you have to watch out with that upslope flow, because we know from studying Colorado tornado events that a 55 dew point, whereas maybe in central Oklahoma it wouldn't quite get it done. 55 dew point in Colorado is more like 60, 62 degrees of dew point. So due to the elevation. So I think that played a role, and we can talk about that a little bit more in a second. But we had very moist upslope flow here. You can see the winds out of the east and even just barely north of east here. So again, moist flow going up the terrain here probably aided in the lift that allowed these storms to get going. So let's go ahead and take a look at our background flow. So here's our 500 millibar flow. We really did not see, I mean, if you look at this map, you're thinking, well, southwest Kansas, there's really nothing there for flow. We have 15 knots of 500 millibar flow. You just don't see that very often with tornado events. But we do, it looks like we did have a little bit of a short wave up here. The main flow displaced up here in the northern plains into the Montana, Wyoming area, into the Dakotas, around this big upper trough here, centered over southwest Canada. But again, not much flow down here in southwest Kansas, 15 to 20 knots. Does look like we had a little bit of a short wave though. Yeah, there you go. A little bit of a short wave here might have aided in getting those storms to form. Little bit of vorticity maximum there in southeast Colorado. Ahead of that could have aided in the synoptic scale forcing to get storms to go, along with that sort of upslope flow that we just talked about. Now at 850 millibars, let's see. So we have, again, very moist flow, kind of a bulge here in our moisture profile here in western Oklahoma. And sort of lots of moisture wrapping around the backside of that surface low. We can take a look at the surface pressure chart here real fast, and this is at 0Z. We do see some evidence of that surface low there. Broad sort of cyclonic flow out here in the eastern Texas Panhandle into western Oklahoma, and you got lots of moisture wrapping around the backside of that low into southwest Kansas. But as far as our low-level jet goes, we can see here, this is at 0Z, not much of a low-level jet, 5 to 10 knots here out in Oklahoma into Kansas, and that did not really increase a whole lot throughout the evening hours. So if you're looking just at the wind profile alone, and we can look at our sounding here, this was the observed Dodge City sounding. Get some of the parameters on there for you. This was the observed 0Z sounding that was launched last night at the Dodge City office. Again, this if you look at this profile, take it at face value, this is not a tornado profile at all. These just weak, sort of chaotic winds here in the low levels. 10 knot east-northeasterlies at the surface. We did have a little bit of turning, I guess, up to about 10 to 20 knots up at 500, but again, 10 to 20 knots at 500 is just not something you see with a lot of tornado events. We also have lots of dry air aloft, so dry air was likely to get entrained into any updraft that formed, which was likely why the models, the cams, were not showing sustained storms here in southwest Kansas. Lots of dry air to be entrained into those updrafts, and as a result, storms would probably be short-lived and just really not a lot of tornado potential out of these. Spreads at this time, 90 over 67. That is a little bit on the high side, but can get it done. We did see, though, on our surface map that here, this station right here, Garden City, I believe, 85 over 67, 89 over 68 here. So definitely in the realm of possibility as far as temperature dew point spreads go. And again, when you see this kind of dew point and you have upslope flow and this sort of little bit elevated terrain, though that 67, 68 dew point is going to act more like 70, 71 degree dew points. A 70, 71 degree dew point. So The moisture profile was pretty good in the low levels, but again, lots of dry air aloft. Just a weak overall weak profile in the hodograph. Um, if we did get storms to go, I would expect to see large hail. We did have a lot of instability, large CAPE, about 3,000 joules per kilogram of CAPE. But this dry air aloft would promote, and I guess marginal temperature dew point spreads a little bit high, would promote downdraft potential, downdrafts in any storm that did form. So you would likely get microbursts and outflow that would undercut any storm that formed. Again, we can continue to look at some parameters here. Take a look at the overall environment. Again, we saw that we can take a look at downdraft CAPE to kind of confirm our theory that the downdrafts would have been favored here, and absolutely, we see lots of downdraft CAPE here in southwest Kansas, above 1,500 joules per kilogram, which is well into the range for downdrafts. That's something you see in the monsoon season in Arizona in the summer. So downdrafts definitely should have been favored yesterday, and likely would have undercut any supercell that formed in any tornado genetic processes that would have taken place. Bulk shear overall, we saw fairly weak overall. You can see here's our 30 contour in southwest Kansas. We're sub 30 knots of shear down here, so very weak shear. And our storm relative helicity, effective storm relative helicity, again fairly weak. We did see some reflection of that, maybe 50 to 100 knots here, which is definitely very marginal for tornadoes. You could definitely see some supercells out of that. This wind profile I could see indicative of some supercells, given the sort of marginal shear effective bulk wind difference of 31 knots here. But again, fairly straight hodograph, not much curvature at all, fairly weak winds, indicative of maybe some large hail, but mainly downburst winds. So what the heck happened? Let's try to deconstruct this storm. Nash from Nashville, he does a lot of good stuff here with radar scope. And so this is his hyperlapse, as he calls it, of the radar, the reflectivity and velocity yesterday. So we can see here our storm fires, and then it splits. So we have our initial storm, kind of a clustered sort of multi-cell mess, and then you get this storm, these two separate storms, as the cluster undergoes a split. So you have your left split there, likely a hail producer, and then this right split was the storm of interest. And we can see here that it starts to dive south. Again, the motion is very slow, but I would say somewhat to the east northeast or northeast. And then look at this. What happens here? We get these showers to form to the south of it here. They get pulled into this storm, and then you get kind of a storm merger there. And then this storm absolutely dives to the southeast. So it's moving east or east-northeast. Merger happens. It moves extremely to the right of the mean flow. And that is likely a contributing factor to tornadogenesis. You had your storm motion. Let's take a look at what our storm motion was, our bunkers right moving storm motion. So bunkers right was actually, let's look at our effective bulk wind difference. So we had our mean wind, effective bulk shear. Bulk shear vectors, again, is a good proxy for sort of storm motion, if you will. 214 degrees at 4 knots. So very slow storm motion, 214 degrees. That would be out of the south-southwest. Our bunkers right motion is 302 at 14 knots. So again, pretty slow storm motion, but 302 degrees would be just north of due easterly motion. Or just, excuse me, the storm would move just south of due easterly motion. So a little bit to the southeast. This storm was even farther to the right of that, it appears. it looks like it's moving more maybe at 320 degrees, 315, 320 degrees. So it was moving even farther to the right of the bunker's right storm motion. So when we have a storm that moves farther to the right, here's our right moving bunker's right motion right here plotted on our observed photograph at Dodge City. We have that probably farther to the left, probably 320, 25 degrees maybe. So we likely had a little bit more of a right-moving storm than what happened. So the helicity was maybe a little bit greater than what we see at the surface here. The effective storm relative helicity a little bit greater than what we saw from this observed sounding, because the storm is moving a little bit farther to the right. Photographs enlarged a little bit more. Your effective photograph is enlarged a little bit more. And so we could have had a little bit more low-level shear as a result of this splitting storm and this storm diving to the southeast. So this storm continues to go on, and then it continues to travel to the southeast. Then near Satanta, it produces the tornado report. You can see a well-defined hook with this, well-defined hook, even a little bit of a donut hole there maybe. And this was producing a tornado at this point. So it's hard to say, this, and as it moved on, it died pretty quickly. You can see the outflow starting to undercut, like we talked about. There's our outflow boundary undercutting the mesocyclone there. So any tornado potential was pretty much going to be brief, and the storm pretty much died after this as it got undercut. So here's the velocity image. We can see not much at all, and then finally, just to the east of Moscow, we see a ramp up in velocity, our velocity couplet here, and it becomes really strong right here. It wasn't tornado warned at this point. Very strong couplet though. Tornado was on the ground at this point, and it lasted for a few scans here, and then it died. And one thing to note here is look how far to the southeast this storm is moving, and then after the tornado happens, it takes a big turn back almost toward the mean flow. Remember, our bulk shear vector was sort of south-south west, out of the south-southwest. Of course, this is not quite moving to the northeast, but you can see it was moving so far to the southeast, and then it just takes a huge turn back to the left as it dies. So that right turn definitely, I think, had something to play, had a big role to play in why this storm produced a tornado. Otherwise, if this storm would have continued moving to the east, I think this sort of profile would have been realized. Very weak, low-level helicity, but I think since you had your storm moved so far to the right of the storm motion vector, the Prague storm motion vector, you had a little bit more low-level shear than was expected. And combine that with our upslope flow, again, our dew points probably acting like low 70s dew points here. This kind of your typical high plains, sort of weak shear sort of setup. We see this a lot in eastern Colorado in the late spring, early summer. You get sort of terrain influences where your background flow, your background wind shear is fairly weak, but your storms, in this case, your storms move far to the right of the mean wind, and with terrain influences in there, you get some big-time supercells with tornado potential out there in the summer. This is kind of the same thing here. Again, a little bit of an elevated sort of terrain feature here in western Kansas, so you get a little bit of extra lift. Your dew points are a little bit higher than what maybe you'd think they are at the surface. At first glance, and you get supercells, and in this case, very much a right-moving supercell, and you get a tornado. And this is not an uncommon sight to see in the late spring, early summer months, early summer time frame in the high plains. This is from Cameron Nixon. He's the hodograph expert, if you will. He has listed a couple of other sort of marginal LCL, high LCL high cloud base but weak shear events. Simla, Colorado, 2015. The Laramie, Wyoming, beautiful hour-long tornado in 2018. Bethune, Colorado, 2019. And if we take a look, this is a RAP forecast sounding from about the time of the tornado. Again, kind of marginal temperature dew point spreads here. But here's our wind profile. Pretty much a straight hodograph, but maybe a little bit of curvature in the low levels, but very weak winds. This is from Simla, 2015. Produced multiple tornadoes, some at the same time up in eastern Colorado on the Palmer Divide. Again, look at that, weak winds all the way throughout the profile, but some turning and very nice upslope flow in the low levels. And you get sort of this long straight hodograph with just a little bit of curvature in the low levels, and it's enough to get it done. This was from the Laramie tornado in 2018, kind of the same thing. Weak winds in the low levels and all the way through the profile, but you get very nice upslope flow. You get kind of a weakly curving, but mostly straight hodograph there in its entirety. Kind of the same thing with this tornado event here. So, you know, it's hard to say. Looking at radar last night, there could have also been a boundary in play. It's very difficult to say if there was a boundary in play. It looked like on some of the scans, I was looking at the radar last night, I should have taken some screenshots of it, but there may have been a residual sort of boundary here. But, you know, that is going to be hard to say. We'd really need higher res data than this to really get a good picture of that. But this outflow boundary could have kind of lingered. This western portion may have stalled out here in southwest Kansas. That could have provided a wind shift boundary for these storms to feed off of. I don't know. I would call this more a dry line bulge as moisture wraps around the backside of that low. Could you argue this is a wind shift boundary? Yes, you could. And you know, it's something oriented like that, northwest to southeast. That storm was moving right along it. So if this was indeed a wind shift boundary or some residual outflow boundary, very well could have taken advantage of that. But again, we would need a little bit more high-res data than we have now to really decipher that. But you know, all in all, a very interesting event. Definitely wish I would have been there. Just a beautiful tornado there with great supercell structure. Again, very small base there to this supercell. Very, very compact supercell structure. But southwest Kansas shows why it's one of the best places to chase in the United States last night. Very unexpected tornado event, but a very interesting case study. So, you know, all in all, I think terrain definitely played a part in it. The fact that the storm moved well to the right and underwent that little merger there with those showers to the southwest of it, that could have played a role. Storm dove to the southeast. That likely it sort of increased the sort of effective shear in the low levels, effective helicity in the low levels than just what we saw on our observed hodograph. And you know, when you have upper 60s dew points in southwest Kansas, you always have to pay attention. So, very interesting case study. Hope you enjoyed this case study. If you have any comments or questions about this event, feel free to comment in the comments below. Definitely would like to discuss if other people have thoughts about this event. It's definitely one that we should understand and look for as chasers to not miss these really nice tornado events the next time we see a day like this coming up. So thanks for watching. If you have any comments, again, comment down below, and we will see you under the next mezzo.